Hello everyone. In this class, in continuing with the previous class on drying operations, we'll use the concept that we have learned to solve some simple numericals. Let's do it. Let's go ahead. So in our previous class, we have learned some definitions about dBT, WBT, humidity, relative humidity, right? So let's make use of those equations or the concept used through some numerical. So the numerical is like this. You can pause the video, you can note the numerical. I'll read out for you. Wet air has moisture with a partial pressure of 12 mmHg at a total pressure of 1 atmosphere and dBT 25 degrees Celsius. So you have wet air, the partial pressure of moisture is 12 mmHg, so we need to convert it. Total pressure is 1 atmosphere, both the pressures are different units, then dBT is 25 degrees Celsius, right, dry bulb temperature. If the vapor pressure of water at this dBT, at this temperature, vapor pressure, that means under saturated condition, is 24 mmHg. You are supposed to calculate absolute humidity, relative humidity, percentage. In fact, it is a percentage of this fractional value of the wet air. So let's take 1 kg of the dry air as the basis under standard condition. So the dBT here is 25 degrees Celsius, total pressure P is 1 atmosphere. I'll convert it to Pascal. Then partial pressures, let me write it for moisture as well as air. For moisture, I'll write it as Pw, the notation. For air, I'll write it as Pr, notation. For moisture, it is given as 12 mmHg as the actual moisture vapor pressure. Sorry, yeah, it's moisture partial pressure. It is given as 12 mmHg here. mmHg means we have to convert to Pascal. How do you do it? 760 mmHg equals to 101325 Pascal. 12 mmHg is equal to how much? Right? Using that concept, I can calculate, and it is around 1600 Pascal. For air, it is total minus the partial pressure of moisture. 101325 minus 1600, that is 9975 Pascal. Now vapor pressure is at saturated condition. It is given as 24 mmHg with the same calculation. Same way, using the same concept, you can calculate and you can find that it is 3200 Pascal. Absolute humidity is given by the definition of mass per mass of moisture per mass of the air, dry air, right? But here we are given with the partial pressures. So given the partial pressures, we can write it as 18 into mole of water divided by 29 into mole of air. And we also know that mole of air by mole of water vapor by mole of air, we can replace it with the partial pressure ratio, because for an ideal gas, partial pressure fraction ratio, right, partial pressure ratio is same as mole fraction ratios, right, mole percentage. So we can make use of that concept here. So it is yeah, substituting the calculated values into this, you get absolute humidity as 0.01 kg moisture per kg dry air. So from where this unit has come, this is the standard unit of H. It's either gram moisture per gram dry air or kg moisture per kg dry air. Sometimes in the books, that is references, to make this as a bigger number, because 0.01 is a very small number, right? So to make it look bigger, you can write gram moisture per kg dry air, right? In terms of that, if I had to convert it, 0.01 kg is 10 gram, right? 0.01 kg is 10 gram. So I can rewrite this as 10 gram moisture per kg dry air. That means if I consider 1 kg of dry air at 1 atmosphere pressure and 25 degrees Celsius, right? It has a moisture 10 gram. So what is the total moisture weight, total weight of the air now? 1 kg dry air plus 10 gram of the moisture. So it is 1.01 kg is the weight of the wet air. Let us look it in different way. Let us see it in relative humidity. Relative humidity means what should be the maximum possible capacity to hold the moisture and what is it holding presently. So we can write it in as a ratio of vapor pressure, partial pressures. Partial pressure under present condition, partial pressure under saturated condition. Partial pressure under saturated condition is also called as saturated vapor pressure of the moisture, right? Which is 3200, and presently it is 1600. So it's a 0.5, and a percentage scale we can write it as 50%, right? So the percent relative humidity here is 50%. So that means considering its capacity, it is just 50% full. 50% more you can fill it till it reaches its dew point, or till it is condensing, till the air condenses the moisture. Still you can add up 50% of the moisture to it, right? Let's make a modification in this problem. Same data, let's make a modification to analyze different properties of the air. So let us use the same data, but the question is you have to calculate heat capacity, that is CP, and humid volume. Humid volume is meter cube per kg. 1 kg of air consists of how much volume? Okay, of moist air. The basic data is given. Specific heat of air is 1000. For steam it is 1880. Okay, it's in joule per kg Kelvin. Let us take 1 kg of the dry air at dBT, total pressure condition. Already we have calculated H is equal to 0.01 kg moisture per kg dry air. Total wet air is equal to 1.01 kg. Specific heat and the air and moisture are given to us, 1000 and 1880. Right? Let's go ahead and do the calculation. So the heat capacity of air will be equal to heat capacity of dry air plus moisture. Together you have to take. Now here the dry air is 1 kg of air. Moisture, it depends upon how much moisture is present, that is 1000 gram, 1 kg of dry air, and for H it is 0.01 kg, right? So the corresponding specific heat I am multiplying it. This is the not the average, it's summing up their actual values. So its Cp will be equal to 1018.8 joule per kg air Kelvin. So kg air I have used a word. In fact, you can write, we generally write as kg dry air. Okay. So even though the quantity is for the moist air, we write it as kg dry air, because when we do the analysis later, we use only kg dry air as the basis for our calculation. To cancel out the terms, it will be easy. Anyways, this detailed design calculation we do not come across. For timing, it is sufficient for you to understand that we usually write as kg dry air even though the calculation is for the whole moist air. Okay, so because this kg dry air, when I mention, it is attached with this humidity value. Okay, it is attached with this humidity value, so that humidity value takes care of the correction over there, right? So let's not bother about that particular concept as of now. Another thing is humid volume. So to calculate humid volume, we need the volume of dry air and moisture. We'll denote it as V air and VW, and with a humidity value coming in between. Now look at this, air and moisture both, I'll consider it as ideal gas. Molar volume, PV is equal to RT, we know the equation. So V is equal to RT by P. Now this is in a molar volume, on a molar basis, right? Meter cube, we get it, meter cube per mole. For 1 mole it is, so it is meter cube per mole. So for mass basis, if I have to convert it, it will be RT divided by P, and the denominator I have to consider molecular weight, that mole I have to convert it to gram. But this density volume what I consider, it will be meter cube per gram. But I want meter cube per kg, so I'll multiply with one constant, that is 1000, right? So if I take 1000 RT divided by PM, it will be meter cube per kg. Okay, let's go ahead. So using this equation, RT by PM and 1000, right? RT divided P into M air plus H RT by PM into 1000. I'm considering that 1000 for multiplication from a gram to kg. All right. So taking the common terms, 1000 are taken out. RT is common in both the equation. Denominator P is also the same thing. So you end up with, in this first term for the air, 1 by M, 1 by molecular weight of the air, plus H divided by molecular weight of the water. Otherwise all other terms are constant. Alright, so it is in bracket 1 by M air plus H by M water, molecular weights, and humidity value coming into picture. Substitute all the terms, you get 0.856 meter cube per kg dry air. In fact, we write it as kg dry air, as same concept over here. Now look at this, density of air, any gas, is around 1 kg per meter cube. Just to give you an idea whether you have gone wrong, or just as a cross check, density of air usually is 1000 times lesser than density of water. Density of water is 1000 kg per meter cube. So the density of air is 1.2 kg per meter cube. That's nearly less than 1000 times. Now humid volume is just the inverse of it. Look at the unit. It is meter cube per kg. Here it is kg per meter cube. Just invert it, right? This is an approximated value. Exact value you will have to calculate and invert it. Alright, that's the density. Now humid volume is just approximately a reverse of it, and usually ranges in between 0.8 to 1. 0.8 to 1. So you won't get a value more than, usually very rarely you get 1, possibly it may not be, or very less than 0.8 is also rarely. Usually get in between 0.8 to 1 meter cube per kg. Right, that's a cross check for you. Yeah, that's it for this class. Thank you.